Alright guys, in today's video I'm going to take you through some problems with multiple diagnostic interface tools. I've actually got three here that have three different problems. And I'm going to show you what those problems are and how you go about diagnosing the root cause of that. So let's start with this guy right here. Just going to power him up, and you can see during the power up he is going to air out with a particular failure case. Now this is a clone device, but this type of problem could happen on regular ones, on real ones too. So it stays at this first part of the post for an extended amount of time. Normally this is a very quick check, and then it should move over here as part of the power-up test. But it's staying here for a long time, so it's having trouble, and then it jumps over here, and it jumps over here. And I don't know if you could hear that, but it has a couple of beeps, and then it goes over to power. So that's what's wrong with this one. Now this one's got a different symptom. This is a genuine one. Let's plug this guy in here if we can see how to put it in. So this guy also sits in this position for a little bit, and then he jumps over here. And then he airs out without a beep. So this one's got two problems. Whatever's causing it to fail the power on self-test, and then the beeper or the speaker is not going off before it jumps over here. And then this last guy, also a genuine one, he starts off over here, and then jumps over here, and this is where he stays. He never exits the test. At this point, this particular one is hung. So what I'm going to do is I'm going to show you, so what would you do to try and figure out what's wrong with these? Now this is not really much into DIY as an owner of these. This is really more for the audience of an electronics technician, but some of this might be useful to you and you might find it interesting. But let's go to the next step here. So how we can figure out where are these failing during the power on self-test. Alright, so let's do the first step of diagnosis. I'm using a Mac here, but you could just as easily use Windows. And I'm using a Keyspan USB to serial port adapter. And then I've got this custom-made cable here, and I'll share you information later in this video how you can make your own. DB9 serial to mini DIN 8 connector. So we're going to hook this up on our serial adapter. Just tighten down so it doesn't come off on us. And then on these MDIs, there's a debug port on the end. That's a mini 8, and it's used by the manufacturing line when they're building these, and we can use that to help us diagnose what's going on. Get this lined up properly. And then I'm using on this Mac, I'm using a program called CoolTerm, but you could use something on Windows as well. And we're running 38400 for the baud rate, and then 8N1 would be our configuration settings. Going to connect up to the USB adapter. And at this point, I'm just going to plug the power in just like you saw before. And you're going to watch the screen. So now what we can see is we're going through the boot up. This is called U-boot. It has an embedded Linux on these things. Coming up, running the kernel now, which is the clone that we're doing first. Mounting the file system. It's accessing the SD now, and here we go. So there's our error on the post. So it says an FPGA error. And that's probably all we're going to get. So it finds a defect in the field programmable gate array. And then it continues running everything normally. But with that chip dead, you can't use the tool. You can't use it to access anything. All right, so at this point she's loaded up. So let's go over and see what the next one is. So we'll come over here and we'll unplug this guy. And we'll bring candidate 2 over here. And then we'll clear this data. And then I'll plug the power in this one. And we can see what the failure condition is on this real MDI and what it's getting hung up on. So booting the kernel here. Okay, post failed. Now in this case, it doesn't print out any error messages. So we got past the FPGA portion, and then it failed after that. At this point, it's just continuing on with the rest of the boot. And at this point, it's done booting. So that's all it had. Now, this one's less helpful to us. We already knew post failed because we had the red light, the red LED light come on, and it told us there was a problem there. We were hoping it would zero in on the exact chip, but it doesn't. So all we know is that post failed. Typically, when post fails, though, I'm going to show you how you can zero on what that is. All right, so let's do the third candidate. So let's come over here. Let's take this guy here. This is the one that is our third one that's getting hung up on this one. I'm going to come back over here again. We're going to clear the data, and I'm going to power this guy up. So he's booting up. And what we find on this one is we never get past this step of booting the kernel. So this tells us a couple of things. One, we never even ran the post. We never even got the kernel booted up successfully, and the whole hardware device is locked up. So this is a problem that's more fundamental, where the processor on board is attempting to access some other piece of hardware inside the device and is getting a hard lockup, so it's dead. All right, so there's the information we've gotten with this tool. So this is a handy tool to help zero in on stuff. You can find all kinds of things like UART errors and post, memory errors, that sort of thing that can help you zero in on what the problem is. At this point, we got to take them apart and kind of diagnose from there. So we'll start with our first case, and we'll get this guy taken apart, the clone, and I'll show you through part substitution how we confirm the diagnosis. All right, let's take apart this clone one first. I can already tell that the screws are a little stripped on this one, so we might have some trouble getting it out. Have to kind of do the tool cocked at an angle. These all should be 2.5 millimeter Allen head type screws, socket head cap screws. Now this type of clone, these screws actually don't go all the way through. They got some kind of convoluted setup where you don't want to try to pull them out all the way. I'll show you as soon as we can get it to separate. Not quite enough yet. That one looks like it might be ready. That one's ready. That one looks like it's ready. Maybe not. All right, there. So this convoluted setup I was alluding to is, you can see they've got these kind of nuts and spacers that they've stuck in here for their design. So you just want to be careful you don't let all that fall apart on you. All right, so what do we think the problem is with this guy? Well, so this guy said it was an FPGA type error. Well, let me tell you, I ran that test a couple of times and I get different results. Sometimes I get the UART failing and sometimes I get the FPGA failing. So the first thing we're going to give a try on is we're going to take this CPU daughter board out, or this MCU daughter board out, and we're going to swap it with a known good one to kind of confirm the diagnosis here. Come over here and power back up again. And let's see if we get a different behavior now. Nope. So that's not our problem here. So now that tells us conclusively, this is typically where you might find some errors on this board here. This board contains the brains of the whole thing. So over here is the microcontroller, or the MCU. This is a Marvell PXA 270M running at 520 megahertz. This is technology that Marvell bought from Intel back in 2006. You can't get these Marvell chips, so even if you have a problem with it, you can't source a replacement. And they have different internal voltages than the original Intel ones. I'll put some information in the description about the differences between the two. So it's not like you can pull this off and stick a new BGA chip on there to repair this. Plus the cost of it, right? This clone altogether, even if it was working, might be worth at most $75, right? So this chip alone would run you over 50. Next to that will be a flash, an Intel flash chip, 16 megabytes. This holds the core operating system when it boots up, and this is where the post runs from. All that's over here on this SD card is the file system, and then all the utility programs that comprise the functionality of the device. All the really smarts of it are right here. And then there are 4 SD-RAM chips. On the clones, no telling what brand they are. On the original ones, they're going to be Samsung. A total of 128 megabytes of RAM. All right, and that's all there is to this. But in this case, it's complaining about the FPGA. So that's going to be on the other board. So we got to get this assembly out further. Let's get our little hat for the power switch out of the way. So we're going to have to go ahead and just loosen this up a little bit more so we can get our finger in here and separate these two. Right, so this board here, you can tell it's a clone, right, because it doesn't even have the Wi-Fi holder soldered onto here. The FPGA is on the other side of this board. And so in this clone, in order to get this out, we have to undo this whole contraption they have with these nuts and screws. It's a PETA to separate all this. And there's the FPGA. Now on these clones, for some reason, this is a very early style clone, so I guess they were afraid of other cloners copying their clone, and so they've etched off all the markings on the chips. But this is typically an Altera Cyclone FPGA. And so this whole board here is at fault for the problem that we're getting. So that's this one's diagnosis, this board here. So what could you do to repair it? Well, you might want to take the time to go check all the coils, diodes, and resistors and make sure nothing's open circuit there or shorted to ground. It's not going to be a problem with any of these relays or any of these buffers that's causing this kind of problem, but you can go through and do the basics and check for any shorts to ground. But it's most likely going to be that this chip right here has failed. And it's not like you can replace it, right? Because you have no way to program it. It would have originally been programmed at the factory through these terminals, and when we open up one of the real ones, you'll see that these are populated. On the clones, they were probably programmed before they were manufactured. And then they get updated through the recovery process. When you do an MDI manager recovery, this can be reprogrammed. But I don't know that it can be soldered in blank and reprogrammed. We might give that a shot, though, to see, just as an experiment. But let's move on to the next one. So we're going to kind of move all this stuff out of the way on this guy here. And we're going to move on to our next one. So that one's diagnosis is the FPGA board shot. What about this guy? So this is the one that also stayed for a while and then reported an error. And this is a real one, so it'll come apart in the typical fashion where you just take these screws out. None of this nut and spacer mess. All right. There's the top cover. Let's get our little power switch out of the way. So let's see if that is the problem here. So we're actually going to take the real, genuine board out and we're going to test it with one of the boards from the clones, a really good clone. Now, a really good clone is exactly the same chips that are used on the original one in exactly the same layout. I mean, if you're going to clone something, clone it exactly the way you find it. And the company that I pulled this out of does that. In fact, I believe the top quality clones, and I've done a review on these in the past, are absolutely perfect substitutes to the real ones. Now, what you have to do, though, is a real MDI is going to have this stud here in the way. And so you'll notice that these are slightly taller by just a millimeter. And so what you'll end up having to do what I'm doing now is you have to get a file a little tiny notch in there so that it'll clear that stud and you can actually get it to fit in there. All right, let's see what this guy does with a new board. Okay. Proceeding through what looks like a normal power on self-test now. Nope, still crapped out. So in that case, it is also not this board. So why is showing you these boards? Well, because sometimes the problem is on these boards, and that's about the only thing that you can repair yourself. If you look at these, you can see, whether we look at the real one or the clone one, they're densely populated on both sides. And if you're going to have to replace this BGA chip, it's not available. So if it's bad, you're done. There's absolutely no way to repair this. If you could source the chip and you had the right equipment, you could then replace it. Or if it was just a case where it's not seated properly, what can happen is there's little tiny solder balls under here, and they can, in some rare situations, become dislodged. And you can reball the chip and replace it. But if the chip is bad, reballing is a waste of time. And even if you did go through the reballing process, if you didn't have the special equipment, this has to be put into an oven and heated at a particular profile in order not to damage this device, and done in such a way that all this other stuff doesn't end up falling off while you heat it up. This will run you about anywhere from $150 to $225 to get done. I know because when I hit repairs like this, I outsource this to somebody local that does that kind of work, and so I know what they charge to run it through, and then they x-ray it to make sure it was a good reballing of this and reseating onto the board. So for something like this real MDI, it only is going to retail in its current state, because this is obsolete with the MDI-2 out, for around $350 or $400. So again, this kind of repair is just not cost effective for the same reason as the clone. So if we had been able to repair it by swapping out this board, that would have been a possibility. Sometimes you can find these boards like on AliExpress, and that would be a way to repair it. But in this case, we again most likely have the problem is the FPGA board. But we're not 100% sure. So what we're going to do is we're going to do a different test here. So I'm going to pop this guy out. And we're going to separate this just like we did with the clone. Just kind of get our finger in here and slowly work these connectors loose. And then we've got this board here where now you can actually see it's an Altera Cyclone 2. And that's the FPGA type. So I just want you to see that where it hasn't been like ground off by the cloners. What we're going to do is we're going to try putting this board in to this one, and we're going to see if we get different behavior. I'm pretty sure we will. So let's see. All this is on the real ones, it holds the USB cable. Sometimes they have those, and sometimes they don't. But I just thought it'd be useful to share with you guys ways you can go diagnose what might be wrong with these. A lot of times people think, oh, as long as it's just a red light, it's just an SD card problem. And it's not. It's absolutely not. In many cases, it's a very bad hardware problem that's just not repairable. All right. And by the way, these are not mine. I just happen to have accumulated these, picking them up from people where they were defective and getting them to experiment with. Let's take this board and replace it with the one from the second one we looked at. Make sure we got that on right, and let's see if we get different behavior out of this guy swapping those boards. Remember, this is the one that gets hung at this test here. Well, there you go. This one's now ready to put back in service. So in this case, this FPGA is also bad on this original MDI, and we've just confirmed that by swapping it from the other one. However, on the other one, we know it's not the daughter board, so it's got to be this board. So this board is bad. Something on this board is shot that is causing a problem. So this at least is a way you can narrow down of the 3 boards that are involved. The microcontroller daughter board. This I call the computer interface board because this is where your USB and Ethernet jacks are going to be, as well as that debug port that we tapped into. And then this last one is the vehicle interface board. All of the protocols for talking to the different vehicles are implemented in this FPGA chip. So that is what's wrong. So out of all 3 of these, we now have one that works. And that's another reason why I think it's worthwhile, to pick up defective of these. You see sometimes on Facebook Marketplace or eBay, and that's where I got these. So you can end up getting parts enough to get one that's fixed. You can go through and test it out with GDS2 and SPS2 and verify it's okay and put it back in service, or resell it, or what have you. Now there are some differences I'll show you here that we have to keep in mind. So these 2 boards are not identical. So unlike the clones, they went through a lot of different revisions on these with the real manufacturing. I think we can find out by looking here at the bottom. So this one that works has an additional exposed ground plane around the edge with no solder mask on it. And it's a revision F board. And this one that doesn't work is a revision C board. You can see that, the orientation of the FPGA has changed, right? Pin 1 position has changed. We can see that the board's population has changed. Obviously, this F board is much more robust in its construction. A lot more buffering, probably a lot more ESD. On the top side, also we can see 2 rows here of devices, only 1 row here. So these are 2 different boards, and so mixing and matching them like that could be problematic. What we want to make sure, though, to do that is we want to take a look at these top boards, and we want to see what level these are. And so we can see that this is a G level, and this is an E level. So these boards visibly don't look that different, but something about them is different. And so you definitely have to go through a lot of rigorous testing before mixing and matching the boards like this, because it's possible that, for example, a G board is not going to function correctly with one of these Rev C type vehicle interface boards. There might be something about that makes them incompatible. Although it's electrically compatible and gets through the post-test, it may not be compatible for running through all the vehicle operations. And you might not be able to practically test all that. It might only fail specific types of vehicles and specific operations in SPS2 or specific operations in GDS2 that it would be just too cost prohibitive to exhaustively test. But it might be good enough for the customer who's asking you to fix this to do something like that. So I hope that helps you out. The only other thing else I'm going to do in this video is we will take a gander at seeing if we can bring one of these back to life by reflowing one of these. It's not a repair, right? Because it's very rare that the problem is actually a broken solder ball. It's more often than not either the problem is internal to the die of the device and you need to actually replace it. I mean, these are not like graphics cards in a PC where it's very common to reball and do a repair. These automotive devices are not like that. These things are either working or not working. But we could give that a shot since we've got nothing to lose, and cost effectively we can't do the correct kind of repair. Again, you can purchase an Altera Cyclone 2. You can find those. This probably would run, I would imagine this chip would run brand new, maybe around $35-40. But then how are you going to get it programmed? These are those pins I was talking about earlier. right? And I suspect these are the pins that the factory would use to program this device. I don't know if you put a blank one on here, if when you go through the recovery process, if it would be able to program one that's blank. Because besides the actual programming of the protocols that are in here, there's probably a configuration that's done one time, and that may need to be present in order to do the update. You don't know. So you end up might just making this even worse by trying to repair it. But we'll give it a shot and see if it is something as simple as a broken solder ball. I seriously doubt it, though, but it's worth a shot. All right, so guys, as I was putting these back together the way they were, I just realized, you know, this can't be an FPGA problem with this board, or when we swapped it over to this board, it wouldn't have worked. So I think that I did not have this daughter board seated properly. So let's go ahead and make sure this is back in the failing state that it was to begin with. This is the second one that we had looked at originally of the three. And go ahead and hopefully it will error out the way it did, or maybe it's even going to be a different behavior, because now that we've jostled with it, that's one of the things that can happen on these. You kind of move them around, taking them apart, and the symptoms can change. So now this one's exhibiting the same kind of symptoms as the third one, but I'm betting that the problem here is not this. I think that we just didn't push this down hard enough. And when I say that, I'm talking about the interference with this little pin here. So I'm going to grab this board again, and we're going to try this again. And I actually filed this down a little bit more, this little divot here, to make it go in easier. Let's see if we actually can confirm that it is this board that's the problem. Okay, so it should not get stuck here this time. Yep. That is that. Right, so we got two of them working. So the problem was this daughter board on this one, and the problem is the FPGA card on this one and on the first one. So that's at least a little bit more optimistic. You know, technically between the three, we can get two of them working now, hopefully. And you'd be able to then move forward with that. So again, we're going to go ahead and give a shot on taking the clone board, like I mentioned before. And in this case, we might start with the clone board and see about reheating this Altera chip and see if it does anything to change the outlook on it before we tackle one of the real ones. All right, guys, using the manufacturer's data sheets, and this is really common to everything. There's really nothing unique about this, but just as an illustration, we're going to need to get this up to 217 degrees and then right at 220 degrees Celsius. That's the temperature at which this non-leaded solder that was used in these days would be fully liquid during heating. So that's the target that we're going to want. And they'll talk to you about a reflow profile, and I'll show you that as well. There's some pages in here on that as well. There's also some information here just on some various specifications about the device. I zoom in here, but the main thing we're after is when you look at these balls that are underneath, one of the things that we're trying to do is reliquefy these so that any cracks or damage on them can be rehealed. And you can do this a couple of times. It's called a secondary reflow. And you'll see here the manufacturer recommends against reballing this particular type of BGA, and they give you their reasons down below. I tell you already the reason is financial. For the cost of the device, it's just not worth doing, with the cost of how long it would take in labor to do this. So we'll give this secondary reflow an attempt and see if that is able to repair the problem. Now guys, I thought it would also be good to show you a little blow up. This is a microscopic view of a solder ball underneath a BGA part. Right, here's part of the pad on the bottom substrate. Here's the pad on the device. This is looking out towards an edge. And what you can see is they've kind of cut this in half, and you can see microscopically these cracks that can form through thermal stress over time, both at both the pad and at the device pad, right? The pad on the device and the pad on the substrate. And so when we do a secondary reflow, what we're trying to do is get all this to fill back in, because in this case you still have contact here and here, but what you can have is you can have a situation where this is completely separated and there is no contact. It's very similar to on a much larger wiring system, a cold solder joint or something of that nature. So that's what we're aiming to do with this secondary reflow. Now the last thing I'll show you in here is the importance of having a particular profile. And the equipment I'll show you that we're going to be using shortly is designed to do close to this. It's not, professional high-end stuff because I don't do this enough to warrant that investment. But the key things when you're doing rework profiles, you want to get the bottom heater temperature. When you get the whole board up, you want to get this guy up to a certain level because you're going to need to be in that 217 to 220 proximity that we talked about earlier. So step one, you want to get the board into this 125 to 150C range. And actually what I'll be doing is getting it closer to 180. And then with the nozzle down on the hot air gun, then we're going to take the joints on the device up until the melting range so that we can get to a point where we can just give it a little bit of a little bit of a nudge with a tweezer or a spatula or something of that nature, just to test that we've liquefied everything, and that should be enough to reflow any cracks. At least that's the theory, right? Otherwise, it's going into the recycle bin. This is your last shot to try and repair something like that. And then they talk about some times on that. And then on the back here, and again, this is just the manufacturer information, they talk about some approaches to this as well. And again, this is specifically for doing rework on the board after it's originally manufactured, which is something they would do if you were going to replace the part. In our case, we're just going to use this same technique for a secondary reflow. All right, guys, let me tell you about that diagnostic cable that I was using here. All right, so if we zoom in and we look at this connection here, this 8-pin mini DIN, and you got this orientation here where the D-shell connector for the DLC cable is in this position. When you're looking at it like that, with the writing up on top here, these top two pins, this guy on the right is the receive for the MDI. This is the serial receive pin on the right. And this is what you're going to hook up to the transmit line on the 9-pin coming out of the PC. And then right to the left of it, this pin here is going to be the transmit on the MDI. And of course, you're going to hook that up to the PC's receive line. And then this guy right here, right in the middle row. So this is the top row, the middle row, the bottom row. So you go to the middle row, this guy on the far left, that's going to be ground. You just need those 3 pins, ground, transmit, and receive, and wire them up to the corresponding pins on the PC, and you've got a cable. I'll put a little graphic up in the upper right here, and I'll also put a link in the description where you can get the parts to make this. Kind of prepping our board here. Just want to cover these other components with some Kapton tape just so they don't accidentally become desoldered during this repair process. So we're going to do a secondary reflow as the attempt we're going to make here, like we were saying earlier. It's not worth attempting to reball this guy, but if we can get all of the balls under here to liquefy, there's a possibility that any cracks in there could be repaired with this secondary reflow technique. It's just a kind of a last-ditch attempt given the cost factor of the device involved. All right, guys, just a quick shot of this setup I'm going to use for this secondary reflow. And again, remember, we're not going to bother reballing this. The whole piece of equipment's only worth $50, so it's just not economically worth our time to do that. We're going to use this particular brand of preheater that I have, the INT853A++, because it has pre-programmable profiles for the heating curve. And I'm going to be using a quick 957DW Plus for the hot air. We're basically going to take this guy up to 183 degrees or so preheat. Then we're going to bring the hot air over the top to take it up to the 220. That'll liquefy the solder, and that should get us at the point where we've done the secondary reflow. I'll put you guys up on the stand, and you can see that secondary part when we get to it. All right, so we've got 2 probes, 2 thermocouple probes, one on the top of the board and one underneath the board as close to the device as we can. And then we're just monitoring the top and the bottom temperatures as she heats up, and she's going through this particular curve profile. Just another shot as she's going through this curve. The C is the top probe and the B is the bottom probe. That's just the jargon for this particular product. It's displaying output in Celsius here. So it's going to take it a good 4 or 5 minutes or so to get to where we need it. The secondary check that we'll be doing is we'll be using a just a temperature camera like this, just to see what the actual top of the chip is, monitoring it on our way to that 183 soak point. All right, that top temperature is coming up on where we're going to want to move the air gun into position, the hot air gun rather, with the nozzle that we've got for this particular size device. I'm going to get that set up and I'm going to move you guys over onto the tripod. All right, guys, at this stage we've added some flux all along the edges of the device so that can wick in underneath the balls as we get almost to the point of moving the hot air gun into position. All right, guys, we've got the hot air gun into position. She should liquefy pretty quickly at this point. We're just going to come over and see if we can see movement now that we're at the right liquefaction temperature of the solder. Right there. So you see how the surface tension on the chip is? At that point, we know we've done a secondary reflow. We can shut off the hot air machine. We'll let it cool down to the preheat board temperature. Once it comes down to that, then we'll ramp the preheat board down too, and we'll give it a shot and see if this did anything to fix the problem. All right, guys, let's give this a test. This is the clone board. We put the CPU board that we reflowed up here, that we did that secondary reflow on. I'm just going to put the top on because it's easier to see the LEDs, I would expect, on this. And then we're going to go ahead and I'm going to hook up our serial cable again. And we're going to power it on. And let's see what we get. So she's starting off on the vehicle board test. Now she's moving over to the interface board test. She passed post. And she's ready to go, and she chirped just fine. And now if we come over here and we look on the screen, everything's loading up just fine. So if we go back through here, the most important thing we want to see is right up here, post passed. Right, so post pass. So we fixed this one just by doing a secondary reflow on that CPU board. So what we found on this one, after we reflowed that board that I showed you earlier, as we were putting it back together, what we saw is we had some oxidation on these two connectors that connect these two pieces, these two boards. This is a two-board setup like we showed earlier. So I hit this with some deoxit G5, let that set up and then blow it out, and then we put it back together and we reinstalled this board, and that seems to have done the trick. So this one's ready to go back in service. Now we went ahead and reflowed the CPU board for this genuine one as well. Always have trouble seeing where the little notch is on this guy. To get this mini DIN in here, we'll go ahead and clear the data on the computer, and we'll see. I already put this one back together. So now with this guy, same test, and again we didn't touch the FPGA board, we just reflowed the CPU board. Chirp. Passed post, she's ready to go, and again if we come over here and look at this, post passed. She's still continuing to load drivers and boot the OS, even though when the chirp happens and you get the power on LED, there's a few more things that happen after that. So at this point we got both of these back in service just by doing a secondary reflow on this CPU daughter board. So the only one left is the third one that we confirmed with the swap that we did. It has a genuine problem with the interface board that has that Altera FPGA on it. So let's give a shot, see if we can get 3 out of 3. All right, guys, next up is this board from the genuine MDI. And again, even though the retail on a used MDI, a genuine, is probably $350, it's still not worth our time to replace this chip. So we're going to try a secondary reflow here as well. Same approach as the other one, although we get a couple of complications. We've got a couple of electrolytic capacitors over here that we want to make sure we don't overheat and have them pop on us. And we're probably going to want to Kapton off this set of plastic connectors here just so they don't get damaged as well. But other than that, it should be just like the one we just did. We'll give that a shot and see what we get out of this guy. All right, guys, here's the setup we've got for this board. We've also added a little piece of aluminum foil over those two electrolytic capacitors just to give them a little bit more insulation and insurance so they don't pop on us. They also have Kapton tape on them, as well as all three of the plastic connectors. So we've got the cyclone centrally located so they can get the most of the heat. We'll try to get this over with nice and quick before we damage any of these other components. All right, guys, just showing you a checkup here. We're not quite to the board soaking temperature yet, so we don't have the hot air gun on, but I had to position it beforehand because I don't want to knock the probe out of the way that's next to it. So we're just going to let it continue to ramp up here before we fire it up. All right, the board temperature stabilized. We're going to turn our hot air station on now, and we're going to bring it up the rest of the way to the melting temperature of the no-lead solder that was originally used by the manufacturer. Try to ramp this up pretty quick here. Currently at 185 degrees and climbing. And we need to get up to 220 in order to liquefy this type of solder. I don't think we're quite there yet, but we're just going ahead and give it a little test just to see. Nope, not yet. We have to wait the full cycle. Currently at 214 degrees. Just waiting for it to climb those last few degrees to liquefy the solder. All right, guys, just took a little bit longer than I had hoped for here. But unfortunately, during this one, I can see one of the balls has worked out. So this is a dud. So this one, whatever reason, that little guy right there worked his way out. So that invalidates this repair attempt. All right, guys, so what went wrong here? Why did this repair fail? Well, I can tell you why, and it wasn't the rework profile. If you look at the previous clip, you can see some brown fluid in the right-hand margin of what we were filming, because we had this kind of a orientation of the camera during the previous clip. And at the time, I thought that might just be some flux runoff, but it actually turns out it was underfill. And that underfill obviously had a different thermal profile. And when we saw that ball come out on this side, and I left the other side here, you can see there's actually, it pushed 3 more out right there. So we had 4 balls get squeezed out as that underfill exited. And what underfill is, I got a little picture here to show you. In some manufacturing processes, what they'll do is after the chip is soldered on, they'll have this dispenser come by and inject a material, kind of like a polymer, under the chip that hardens. And this is designed to help deal with not having the situation that we're chasing, where you have to do a reflow. But when you have that, it's really more difficult to rework the part because of that problem. Now, the reason I know it's not the profile is I was working on this other board before this that also has a Cyclone 2, although it's a different part number, and this guy came out fine. So we just basically applied the same profile to the MDI's board, and right when we were thinking it should have been liquefied, it should have been, and that was the underfill that was preventing it from coming out when it should have. And then what happened is it started to push these balls out as it looked for an exit path out of the device. If you remember, this board was kind of sitting at just a little bit of an angle just because of our board heater, so it had a tendency to run up along here. So unfortunately, that makes this a bust because, like I said, right, it's not cost effective to reball this. It's certainly not cost effective to replace it. This particular chip runs about $100. Regardless of what you might see out there online where some Chinese sellers are trying to tell you they can sell a chip like this for $20 or $30, those are usually relabeled, not this actual part. They usually sand this off and they put something else on here, and it's going to be a different speed part or something of that nature. If you're lucky, you might get a part that's been pulled and reballed, and that, if you're lucky, but you can't tell what you're getting there. So, like they say in that song, right, 2 out of 3 ain't bad. We got 2 of these back in service. This one we didn't, because of this underfill problem, and I shared this with you because if you're going to be reworking these, keep that in mind. If I did this over again, I think what I would do is I would let the heat soak a little bit longer at around 185 degrees. I would try to raise it up at more of an angle and try to work all that underfill, let it run out before we actually tried to liquefy the solder. So if I had another shot, that's the technique I would try. If you've had experience with this, I'd love to hear about it in the comments below. Go ahead and tell me what you've done to deal with this particular problem on this particular board with the particular manufacturing process that's employed. If you got questions or comments about what we did today, go ahead and leave those below and I'll try to help. If you found this video useful in getting your MDI repaired, or for yourself or for a customer, pay it forward and hit that like button. I'd really appreciate it. And as always, thanks for watching.